I went out and I asked, does anyone have questions? If they do, let me know. And the response was, not too many questions. In fact, very few. So I'm excited because that means people understand. And with great understanding means high test scores. Woohoo! Lots of A's. Well, that's the hope. All right. So we're actually just going to talk about 3 problems because that's it. That's all I was asked to talk about. Okay. So let's begin. Now the first one dealt with sequences, and it said it's actually one of the practice quiz problems. So it says you have a sequence a sub n, where n equals 0 to infinity, a0 equals 5, and then there's a rule. So this is what's called a recursive rule. Now, the idea of recursion is the idea of you build on what you've done before. So in other words, if I want to know how to get the next term, I say, well, let me use information about the current term to figure out the next term. So here's my rule. If I want my next number, I take 55 times my current number. I add to that 4 times wherever I'm at. So n is an index. It's saying, okay, where are you on your list? Subtract 220, that's a big number. Then subtract n, again, that's where you're on your list, times your current number. Okay, well, as they say, this is a little bit interesting. Now, what do? And the goal is, well, find a sub 57. Now, we're starting with a sub 0. So it would seem to be, it's going to take us a long time. But even worse than that, there's lots of big numbers involved. 55 times something, that's going to make things big. And if you do 55 times something a lot of times, it gets uncomfortably big. So, what to do? What to do? So, let's, before we start, oftentimes when you see something like this, you ask yourself the question, I wonder if there's perhaps a better way to represent this. Because oftentimes there's I don't want to call it a hidden idea here, but there's maybe there's something that we can use that makes our life better. And isn't that what calculus is all about? Making things better? So for instance, you'll notice that I have these a sub n minus 1s. Let's put those together. In fact, since they're common, I can factor that out. I can take 55 minus n times a sub n minus 1. If I pull out a 4 here, and, well, in fact, let me pull out a negative 4. You'll see why in a second here. Then 220 is divisible by 4, leaves me with 55. And then, so as I pulled out a minus 4, plus 4n would leave me with minus n. Aha! No, check it out. 55 minus n. So, what you have is 55 minus n times a sub n minus 1 minus 4. All right, well, what do we do with that? Well, now we say to ourselves, isn't that interesting? 55 is very close to 57. Coincidence? Well, you should always say maybe, but if it's a math problem, maybe not. Well, okay, well, why is this useful to know? Well, notice here, 55 minus n. What we note is that at the 55th index, this is 0. Now, why is that helpful to us? Well, you see, 0 is a friend. In fact, we'll write that down. 0 is friend. It's not your foe. Yes, it's true, you don't want 0 on an exam, but when you're doing a problem, you want 0 as much as you possibly can. Okay, so what happens next? So we say to ourselves, well, let's skip ahead. Let's not do A1, A2, A3. Let's jump to n equals 55. Okay, so in other words, we're getting close to where our target is. At n equals 55, what do we have? According to the rule, it says A55 equals 55 minus 55 times A55 minus 1. 54 minus 4. Do I know what that is? I do not. Good. I don't. But I know this is a number and this is 0. And multiplication by 0. Wow. Powerful stuff. 0 times anything is 0. So we get to sort of skip a lot of work and say, hey, if I start at 55, I have 0. Now, let's do our next one. N equals 56. So what is that? Well, you take 55, subtract 56. You can multiply that by A55 minus 4. Well, 55 minus 56 is negative 1. And A55 is 0, subtract 4. So 0 subtract 4 is negative 4, leaving us with positive 4. Okay, and now our big moment. 57. A57 is 55 minus 57, right? 55 minus n equals 57, times A56 minus 4. Well, 55 minus 57 is negative 2. And 4 minus 4 is 0. And, well, it's hard to recover from multiplication by 0. And therefore, our answer is 0. And we're done. All right, and that was the first problem that people wanted to know about. All right, let's go to the second problem. Now, the second problem is about error estimation. And so what is that? Well, so it actually comes from a homework problem. So we're going to have a function. In fact, it's not just any function. It's f of x equals 1 over 1 minus x. All right, and we're going to do the cubic approximation. And we're going to do that at x equals 0. Now, we can save ourselves a little bit of work. And we could say what? Well, we know what 1 over 1 minus x is. This is our geometric sum. It's a classic. You always know the classics. So we know that 1 over 1 minus x, that's the sum from 0 to infinity of x to the k. So that's 1 plus x squared plus x cubed plus x to the fourth, and so forth and so on. Now, when it's asking for a cubic approximation, it's saying, all right, let's try to understand, all right, what's the worst thing, cubic approximation, what's the third degree? Third degree. Well, you might say, why don't we just come here and just say, let's take everything up to the third degree and ignore that. And that's what you do. You see, once you have a series, if you find a series, it's the series. So this part here at the start, this is our cubic approximation that we're after. Now really that was the easy part of the problem. And in here, we didn't have to do hardly any work at all. It's beautiful. No derivatives, out it comes. Mwah. Now, the interesting part comes from saying, what's the error? And in other words, we want to bound the error. I can spell error. For the size of x is within 0.1. Okay, in other words, we want to look at this cubic approximation. So how do you bound that? Well, what you can say is that the size of your error is at most, if you're doing a cubic approximation, remember, that's another way of saying n equals 3. So you go to your next derivative. So 3 plus 1th derivative. So in other words, the fourth derivative at some point C, we'll get to what that we mean here by that, x minus 0 to the power n plus 1 over n plus 1 factorial. And whoops, I should have said n equals 3, so that's really 3, and that's really 3 there. And here, where we pick the max C. All right, now, in some sense we can say, if we're looking for a numerical answer, we say, look, I want the size of x to be as big as possible, and size of x is bounded by 0.1. So what we'll do is we'll say, all right, I want to do, let's call this expression here for a second m. It's at most m, whatever that turns out to be, times, and here I'm going to replace the size of x by 0.1. So 0.1 to the 4th power. And then we have 3 plus 1 factorial. That's 4 factorial, which turns out to be 24. So then the question is, how do you find m? And the way you find it is you say, well, the rule is look at your next derivative. And now we're like, oh, wait, we didn't take any derivatives. Well, now we do. Okay, so here we go. So 1 over 1 minus x is actually not so bad to take this derivative. So if I look at my function f of x, I'm going to think of this as 1 minus x to the minus 1 power. So f prime of x would be the minus 1 comes down, 1 minus x to the minus 2 power times the inside is a minus 1, and the minuses cancel out. So really that's 1 minus x to the minus 2. The second derivative, minus 2 comes down, 1 minus x to the minus 3 power, and there's a minus 1 that comes down in front. The minuses cancel, so you get 2 times 1 minus x to the minus 3. Third derivative, all right, the 2 is there, minus 3 comes down, 1 minus x to minus 4, and multiplied by a minus 1 on the inside. The minuses cancel. All right, well that's some good news. And now, the fourth derivative, which is what we're after. Okay, so the fourth derivative, by the time you hit the fourth derivative, almost always you switch notation. So instead of using the primes, boom, 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 you say, okay, look, I don't want to keep counting how many prime marks I make. So what happens? We have the 2, and then we have the 3, then we have the minus 4 comes down, 1 minus x to the minus 5, and multiplied by the inside minus 1. So minus, those cancel. And so what we have is we have 24. Divide that by 1 minus x to the 5th. Okay, now what happens here? Remember, my m is about what's the worst case scenario for this derivative. So I want to look at this expression, 24 over 1 minus x to the 5th, and I asked myself the question, what's the worst thing that could happen? In other words, I want to remember that given that the size of x is small, so it's within 0.1, what's the worst? Now we have to think about it. So, okay, let's be careful here, and because we want to make sure we get it right on our first try, because on a test you only get one shot. Notice there's only one x. Now, since there's only one x, we say to ourselves, okay, given that there's only one x, do I want to make this value a large number or a small number? Well, notice it's in the denominator. So, since your x only influences the denominator, we say, if I want a larger number, smaller denominator. So, should I, and all right, be careful here. X can be anywhere, remember, this has negative 0.1, less than x, less than 0.1. Should I have x be closer to negative 0.1, which would make it something like 1 minus 0.1, so that would be 1.1 to the 5th. Or should I have it be closer to 0.1, which would make it 1 minus 0.1? That'd be 0.9 to the fifth. Or should it be somewhere in between, like near 0, which would be 1 to the fifth? The answer is, if I want my denominator to be small, which would make my whole number large, I should choose x to be as large positive as I can. So I want it to be close to 0.1. So what we can get, I'm running out of space down there, so I'll do some work up here, is I can say that m is at most, and this is really the best possible situation. You know, it's the best worst case scenario. Okay? So is at most 24 divided by 1 minus 0.1 to the fifth. All right, or if you like, that's 24 over 0.9 to the fifth. All right, good. And that is using our best possible choice for m. So, putting that down here into m, we see, all right, by the rule, we can say with great certainty that we are at most, and by the way, we're definitely less than by the time we hit this, but that's okay. Less than or equal to versus less than is not a big deal here. 24 over 0.9 to the fifth times 0.1 to the fourth divided by 24. You'll notice that 24s cancel. That's really nice for us. And if you work this out, now 0.1 to the fourth, 0.9 to the fifth, really we can play around with this a little bit, but you can think of this as, in the numerator, this is 1 over 10,000. The denominator, you can think of it as 9 to the fifth over 100,000. In other words, the number, see that 4, that's how many zeros there should be. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 zeros. And now comes one of our funnest things, which is when you have a bunch of zeros upstairs and downstairs, you just get to do the cancel the zeros. Boom, and what do we end up with? Well, we end up with 10 divided by 9 to the fifth. And that's our error, which, by the way, is a relatively small number. And so, when we're within 0.1, which is pretty close in the grand scheme of things to 0, then our error is pretty small. Remember, this is an upper bound for error. It's probably even better than that. So, that's good. That's good. Okay, that was the second question that was asked. So what was the third question? So the third question which was asked was the following. Multiplying series together. So let's just do a quick recap of how that works. And it's actually not so bad. In fact, the philosophy is pretty straightforward. So suppose instead of multiplying series together, I asked you, can you multiply polynomials together? And you might say, yeah, sure, that's not so bad. So for instance, if I had 1 plus x cubed plus 2x to the fourth, and I multiplied that by x plus x squared minus x to the fifth, what would you do? Well, the rule is pretty straightforward. It says every term in the first expression multiplies with every term in the second expression. So, what do we get? Well, 1 times x, which is the x. And then we get the 1 times x squared, which is x squared. And we get the 1 times minus x to the fifth, which is minus x to the fifth. Give ourselves a little bit of space here because I suspect something will happen. X cubed times x. Ooh, now here's something. That's x to the fourth. So I can sneak it in there. Now, x squared times x cubed is an x to the fifth, so there's actually a plus x to the fifth. And then x cubed times x to the fifth gets us a minus x to the eighth, and I'll give myself some space. Now, 2x to the fourth times x is what? Well, that's 2x to the fifth. So we get a plus 2x to the fifth, and then what comes next? 2x to the fourth times x squared would be 2x to the sixth. All right, I can squeeze that in there. And 2x to the fourth minus x to the fifth, multiply that together, gives you minus 2x to the ninth. So you get x plus x squared plus x to the fourth. Here they combine, plus 2x to the fifth, plus 2x to the sixth, minus x to the eighth, minus 2x to the ninth. Okay, so that's what you do. Now, the thing is that multiplying series together works the same way as multiplying polynomials together, but there's one small change. So you notice here I said 1, go term, 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 term. Then x cubed, term, 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 term. Then 2x fourth, term, 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 term. When we're multiplying series together, what we do is work in the powers. In other words, we would say, okay, let's start by saying what would produce a constant term? Well, nothing, because the constant term I need to have a constant and a constant. I don't have that. How about x? X and 1. All right, that's it. How about x squared? X squared and 1. Okay, that's it. All right, not very exciting. X cubed. No way to do it. X to the fourth? Well, where did that x to the fourth come from? We can't have an x to the fourth. Did I multiply it wrong? I hate when I do that. That x plus x, that shouldn't be there. Oh my gosh. I feel silly. Sorry about that. All right, did I miss something? 1, 2, 3, 4, 5, 6. I am missing a term. Which term did I miss? X plus x squared minus x to the fifth good. Oh, there is an x to the fourth. Whoops. I should trust myself, right? Because I can multiply x cubed times x. That's where I get the x to the fourth. Now the x to the fifth is the most interesting because what you'll notice is we can multiply and gather several things. 1 times x to the fifth, x cubed times x squared, x to the fourth times x. And so we're all good. It all comes together. So in general, what you have is when you're multiplying two series together, you might have, and I'll write it generically, a0 plus a1x plus a2x squared plus a3x cubed. And then over here, b0 plus b1x plus b2x squared plus b3x cubed plus ... So constants, then you work on your first order terms, then you work on your second order terms. So see, constant x squared, xx, x squared constant. Third order terms, x cubed, and then x cubed, then an x cubed, then an x cubed, and so forth and so on. In general, what you'll get is you'll get some polynomial where your coefficients, cnx to the n, where the cn is the sum, 0 up to n, of a sub k, b sub n minus k. And this has a fancy word, and it's called convolution. All right, so that's the philosophy. Okay, rubber meets the road. Let's try it in a problem. How would we do it? Well, let's suppose we were asked to do something like the following. So suppose, given that you have f of x is equal to the square root of 9 minus x to the 7th divided by 4 minus x to the 5th, find the 24th derivative evaluated at 0. All right, well, that problem should make you feel a little bit uncomfortable. And you might say, is it possible? Well, certainly there's a Calc 1 approach, which is take 24 derivatives and call me again after, a month or so. And hopefully I didn't make any mistakes. I don't recommend that approach. For one thing, it takes a month. So let's avoid that. Okay, so how can we avoid it? So what we're going to do is say, let's figure out what's going on. Now, whenever you're asked to find a high order derivative, now that we have our tool, we say, if we could find a Taylor series for this, we could say f of x, that's like the sum from 0 to infinity the kth derivative evaluated at 0 over k factorial times x to the k. So if we look at this at the term k equals 24, then what we have is that the coefficient of x to the 24th is indeed the 24th derivative evaluated at 0 divided by 24 factorial. So I am looking for x to the 24th. How do we do that? All right. So let's think about this. All right, let me transfer the function over here. So again, our function here is f of x is the square root of 9 minus x to the 7th. Divide that by 4 minus x to the 5th. All right. So we start asking ourselves the question, have we seen anything that looks like this? In other words, is there any power series that we encountered that had this type of expression on it? Now, you might think geometric, right? Well, the problem is that there's a square root. If it weren't for the square root, this would basically be something geometric-like and life would be good and we're happy. But the square root messes it up. So what does this look like? And the answer is it vaguely resembles the following, namely something to a power. And the rule is if I have 1 plus something to a power, well, that's the sum from 0 to infinity of whatever that power is, choose k, times something to the k. And again, I like to think of it as my something. So in other words, I think of it as there's a box. And my goal is to say what goes into the box. All right. Now at this point you can rightfully say, does it really look like that? And the answer is no, but of all the things it looks like this the most. And the hint that I'm thinking that it might have something to do with this is the fact that I have this sort of power going on upstairs. That's sort of the clue to me that something is going on. So here's one way to think about how to approach this. I can think of this as really two pieces. The square root of 9 minus x to the 7th and the square root of 4 minus x to the 5th. Because I can break square roots up in that way. Or, if you like, I can go even further and I can think of this as 9 minus x to the 7th to the 1/2 and 4 minus x to the 5th to the minus 1/2. And now we're starting to be like, yeah, okay, I see it. It's something to a power. Life is good. But what's bad? Well, that's a 9. That's a 4. I want a 1. Well, that's easy to fix. You see, I can pull out the constants. So if I pull out a 9 here, so if I factor 9 out, well, what do we have? Well, I can think of this as 9, 1 minus x to the 7th over 9 to the 1/2. And if I pull out again a 4, 1 minus x to the 5th over 4 to the minus 1/2. Now, at this stage, you're like, okay, well, 9 to the 1/2, that would be 3, all right. 4 to the minus 1/2, well, that would be over 2. That's a constant. Life is good. We're closer. We got the 1. Now the problem is this is a minus, which should be a plus, but that's okay. Minus and plus really are more compatible than we often think. So I'm going to think this as a minus, as a plus, a negative. And do the same thing, plus, a negative. And now, what do we have? All right, so again, 1 plus minus x to the 7th over 9 to the 1/2 power, and then 1 plus minus x to the 5th over 4 to the minus 1/2 power. Now we can apply our series. So we get 3/2. All right. So we're going to, it turns out the first term is always a 1. So alpha choose 0 is always 1. Plus, I'll have 1/2 choose 1 times minus x to the 7th over 9 to the 1. Plus 1/2 choose 2 minus x to the 7th over 9 squared. Plus 1/2 choose 3 minus x to the 7th over 9 cubed. Now, I'm going to make a little note here. Remember, because it's been a while, I was on the previous page, our goal is x to the 24. Now, notice our powers. 1, 7th power, 14th power, 21st power. The next term is 28. That's bigger than 24. That means everything past that doesn't contribute. And we're going to multiply this by, okay, now we do this term. So it'll be 1 plus minus 1/2, choose 1, times minus x to the 5th over 4 to the 1. And we're going to keep going. And it just takes a while. There's really, it's in some sense, it's a little bit mindless here. It's just applying the rule. And the only thing that we have to pay attention to is, well, when do we stop? And the answer is we'll stop once we for sure know that our next term would not matter. And I see that I did not plan very well. All right, but, whoops, if you check, this will get us up to 25, right? Oh, whoops, that's past 24. Okay, haha, I planned brilliantly. I just didn't pay attention. Okay, all right, so 3/2 times that series times that series. Now, here is our ... plus something x to the 24. ... Because I only want to grab x to the 24. Well, what will there be? There's definitely going to be a 3/2. So there's a 3/2. Now, we start thinking about our powers here. So I have a 1, an x to the 7, an x to the 14th, an x to the 21. Down here I have a 1, an x to the 5th power, an x to the 10th power, an x to the 15th power, and here this is an x to the 20th power. All the other terms, the powers are so big, it exceeds x to the 24th. So I start asking, okay, if I have a 1, is there an x to 23 over here? There is not, so I don't need to worry. If I have 7, is there an x to 17th? No. If I have 14, is there an x to 10th? Yes. Okay, I'll come back to that one. If I have 21, is there an x cubed? No. Which means that the only way I can produce an x to 24th is if I were to take those two terms and multiply them together. X to 14th times x to 10th. All right, so when we multiply those terms together, what do we have? We're going to have 1/2 choose 2 from here, and then we're going to get a minus 1 over 9 squared. Because don't forget, this square applies to the whole thing. Here we're going to get a minus 1/2 choose 2, and then we're going to have a minus 1 over 4 squared. All right, and that's it. That's our term here. Now let's clean this up. Okay, so we get 3 over 2. Now, a 1/2 choose 2. The way you do that is you take a 1/2, and then you subtract 1, which would be negative a 1/2. And now you have two terms. Downstairs, 2, 1. Minus 1 over 9 squared. Well, that's really 1 over 9 squared. minus 1/2 choose 2, so that's minus 1/2. Subtract 1 minus 3/2. Now we have two terms. Downstairs to 1. Minus 1 over 4 squared is 1 over 4 squared. And I seem to want to keep going here because I feel like we're making good progress here. Okay, so we have 3 over 2. And let's see. Let's count our negatives. There's 1, 2, 3 negatives, so there's a negative here. And okay, so there's negative 3 over 2 here, a half, and a half, really. So that would be a 1 over 8. That's a 1 over 9 squared. Here I have a 3 upstairs, and then downstairs a 2, 2, 2, so that would be an 8. And then I have a 1 over 4 squared. Well, the nice thing is the 3 and the 3 cancel with the 9. And so we end up with a minus upstairs 1, downstairs a bunch of 2's. So let's see. That's a 2 cubed, a 2 cubed. 4 squared is really 2 to the 4th. And then we have a 9, so it's a 9 times 2 to what power? Well, it's 4 plus 3 plus 3 plus 1. That would be 2 to the 11th. Also known as 2048. Of course, we all know that. That's no surprise. Now, is that our derivative? And why not? You're right, it's not our derivative. Ha ha ha! Okay, what are we missing? What are we missing? Well, remember, this is the coefficient of x to the 24th. And we found that by multiplying the series together. So this was all about multiplying series together, and how do we do it? Work by the powers, find the powers. We grabbed our term of x to the 24th. Now, if we go back a couple pages, we said, hey, the coefficient of x to the 24th is the 24th derivative of 0 over 24 factorial. And so we can say the 24th derivative evaluated at 0 divided by 24 factorial is, well, negative 1 over 9 times 2 to the 11th. So what we can conclude is that the 24th derivative evaluated at 0 is, multiply that 24 factorial across, negative 24 factorial divided by 9 times 2 to the 11th power. And there you go. It took us a little bit of time. Definitely not a trivial problem, but also we finished it in under a month. So I consider that a success. Okay, well, I hope everybody else is doing well, and the final is coming. So good luck, and we'll see you soon. Bye.